All right, so hi, I'm Eric Grootes. I'm a postdoc research fellow at ESA in the Netherlands, and I'd like to thank everyone else for giving me the opportunity today to talk about this. And I've also been hearing a lot about what happens to gas once it's in the galaxies and how it's converted to stars. What I'd like to focus on is how that stuff actually gets there, and how that depends on the larger scale environment in which the galaxies reside. Right. So while I assume that we all are more or less familiar with this picture of gas fuel in the galaxy, let me briefly rehash. We expect on the one hand gas fueling to be a function of environment in the sense that it depends on halo mass. So if the cooling time scale for gas going into the halo is short compared to the free fall time scale, then we can have very efficient accretion of gas from the IGM down to the galaxy, and that can fuel a very high level of star formation. This is often referred to as cold accretion. Now, if the cooling time scale becomes long compared to the free fall time scale in dark matter halos above 10 to 12 solar masses, then suddenly we build a hot virialized IGM, and the actual rate of cooling of the galaxy is determined by the cooling rate from the hot medium. Hot with accretion, which is thought to be much less efficient. And then as halo mass increases, well, then we expect the cooling rate to become lower, and thus we see two types of dependence on halo mass with of gas fueling. Now, on the other hand, the star formation rate will also be determined by the feedback process of the galaxies that we've been hearing a lot about. So we come to a self-regulated balance between the inflow and feedback, which should be determining the level of star formation that we see in galaxies at the center of the dark matter halos. But, sorry, we also know now since, well, 10 years, or more, that a very large fraction of galaxies actually reside in groups, so more than 40%, and that gives rise to the distinction between central and satellite galaxies. And for satellite galaxies, they're moving with respect to the hot virialized medium of their host group. So they are subject to ramp pressure stripping or strangulation, which is the ramp pressure stripping and the ablation of their atmospheres. And this has led to a widespread expectation that there is no gas fueling onto these galaxies until these two quenching star formation. But while this is generally accepted, we don't have much in the way of a direct empirical reference to deal with this. And that is partially due to a range of observational impediments. First of all, it's kind of hard to get gas contents from large statistical samples of galaxies spanning a wide range of environments. So what can we do about that? Well, how about we invert the Henniker-Schmidt relation to get an estimate of the gas? But there's also another problem, it's the dichotomy in galaxy morphology. Now we know that these different types of galaxies have very different average colors for the star formation rates, but also they largely, by and large, have different kinematics. And there's also the morphology density relation. So the question arises of whether, if I put one of these in a dense environment or in a massive halo, it actually also becomes red because it doesn't see the fuel coming down onto it, or whether the difference is actually more due to properties intrinsic to the galaxies. So if you want to invert the KS, you better know the answer to this question. And then there's also galaxy-galaxy interactions, which we know can impact the star formation rate. But they're also a way of potentially quenching star formation directly, as we've heard earlier during the conference. So if you want to do an empirical reference, what you need, first of all, a large sample of galaxies probing the halo mass function down to this mass of 10 to 12 solar masses. What you need is a tracer which traces the gas content or the total star formation rate on time scales which are small compared to the dynamical time scale of the groups you're looking at. So this is an NUV tracer and also motivates by need control for morphology. And then you need to control for galaxy-galaxy interactions and get some other class selection. Okay, so right. Gamma, which I guess you all kind of have heard about, is a great resource to do this, having an unprecedented characterization of the Grootes environment. And this has allowed us, and their auxiliary data has allowed us to use a very complete morphologically selected sample of spiral galaxies and highly accurate star formation rates due to attenuation corrections to, first of all, define a reference relation for fuel spiral galaxies with specific star formation as a function of solar mass. And the reason you need to do that is because stellar mass is the dominant determinant for the star formation rate. But with this reference in hand, you can look at the main sequence for satellite spiral galaxies in the local universe with the central spiral galaxies in the local universe. And what you see is that this relation is only minimally offset over its entire length with respect to that of the field. And that offset is due not to the entire relationship thing, but due to a population of strongly suppressed galaxies popping up, whilst the majority of galaxies are actually forming at the level of the field. Now, to investigate this, what we've done is to model this with parameterized star formation histories, considering delay quenching models, where you have a delay time, and then a quench, or refueling models, where you have stochastic probability of quenching and then recovery. And, well, we use a figure of merit to see how good our models agree with the data. And what we find is that while we can, in all cases, reproduce the observed distributions, the refueling model does so over a wide range of parameter space and actually performs best, whilst the delayed models require at least delay times before they start quenching of on the order of 2.5 to 3 gigayears. So that's quite long compared to the depletion time scales. And what's more, you see that the actual skewness of the distribution is larger for high mass systems than for low mass systems. Now you can try to interpret this in terms of the gas content of the galaxies. So what you do is you write the differential equation for the ISM mass, inflows, outflows, consumption by star formation, reformulate that in terms of the ISM mass for all terms, and then you identify solutions which correspond to the functional form of the parameterized star formation which we've been looking at. You can then identify these parameters that you have determined from your fits, and this allows you to estimate the inflow rates that these galaxies are seeing. And what you see is that you have inflow rates on the order of twice the star formation rate. So you have a rapid cycle of gas into and out of these galaxies. And this is the case for all environments. And if you then look at the mass budget, you also see that you require gas which is not associated with the galaxy at infall in order to support star formation activity over these periods. So you need to fuel the ISM of these galaxies from the IGM of their host halos at a rate comparable to the star formation rate, but which does depend on how much ISM and CGM can be retained. Right, so far so good. You can go on then to see how this process depends on halo mass in more detail. So this is split at the median halo mass of the sampling probe, so 10 to 13.6. Blue is high mass, green is low mass, and you see there is no significant difference, and they are both offset with respect to the field as we had seen earlier. Yeah, so this distribution looks similar. It only goes away if you take a high mass halo and add AGN to the central galaxy of the group. Not of the galaxies that are determining this relation, but to the central galaxy of the group. And it really is the combination of a high mass halo with an AGN, because if you don't have that, that's what I'm showing you in purple, then you see none of this effect. So let me flip that back and forth to convince you that it really is a distinct effect. Now, then you check out the distributions, and yes, so this is showing the refueling model as a reference that we had earlier, and it's only this combination of central AGN and high mass halo where you find that this peak, which corresponds to just an ongoing refueling of the dominant population of satellite galaxies in these environments, breaks down. Well, for all other environments, that's exactly what seems to be going on. So with that, I'd like to thank you for your time and attention, and close with my conclusions that gas fueling is going on in satellite spiral galaxies, and that this is fueled, at least in part, but likely to a large part, by accretion from gas of the group halo. So the IGN. This gas field is largely independent of environment in terms of halo mass, at least on the scale of galaxy groups. And the independence is only broken if you're looking at massive groups and central AGN, with the central AGN. So this means that our picture of how the gas field works is incomplete, and that hence our knowledge of the importance of gas fielding in the group environment may also be affected by this. And finally, that the color density relation for galaxies seems thus to be determined by the morphological mix rather than by the gas fielding. Thanks.
This is very interesting results. I was wondering if this is true, that there is fueling from the IGN, then you might expect a difference in the metallicity content of those galaxies compared to equivalent central galaxies.
Yeah, that's absolutely true. Well, I wouldn't necessarily say that you wouldn't necessarily expect a difference then, right? Because the central galaxy of the group is likely still also accreting material from the IGN. It would be more that if you switch off the fueling onto the satellites, they should have a potentially different metallicity from the central. But there's of course the question which way that goes, because they're also pressurized, so they may be metal enriched, and the other one actually metal poor due to semi-crystalline accretion. So I'm not sure which way that would pan out, but it's something worth looking at.
It's worth looking at. I think if you compare with galaxies of the same stellar mass which are isolated, then you would expect a metallicity enhancement, if that was true.
Yeah, that's definitely the case, and it's something that we do want to look at, but we haven't had all the metallicity data in hand to do with that at this point in time yet.
If there are no other questions,